in order to do this tutorial, you need this same chart that I handed out to you pasted into your lab notebook. Now you'll notice that the handout that I gave you has an extra row down at the bottom, down here where I'm showing you the cursor. There's an extra row down here. On yours, what you needed to do is to cut that off. So you're only going to have 3 rows on your chart, just like I have here. This chart represents the periodic table. It represents the representative elements of the periodic table. Notice that they are labeled 1A through 8A. What I'm going to do, and what I want you also to do, is to, hold on a minute, let's get some pen action going here. Hopefully yours is a little neater than mine. Maybe you want to use a ruler. And this line really represents the separation, that space you see on your periodic table between groups 2A and 3A. If you were to drop down another row, down here where this line is, that's where the transition metals would fall on your chart. Okay, we are going to use this chart to examine and understand periodic trends. So somewhere on your lab notebook on this page, I want you to make that label to remind yourself what we're doing here. Okay, the next thing we need to do is label the elements, and here's hydrogen. So I'm going to put the symbol for hydrogen in the top left-hand corner and its atomic number on the top right-hand corner. Here's helium, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon, sodium, magnesium, aluminum, silicon, phosphorus, sulfur, chlorine, and last but not least, argon. Okay, we are going to be using the Bohr model to help us understand periodic trends. So the next step here is going to be to draw a Bohr model of the atom for each of these elements, and I know there's 18 of them. So it's a little bit of a laborious process, but I promise you it will make things easier for you to understand in the long run. So here we go for hydrogen. We have this dot represents the nucleus, and here's the first energy level. There was 1 electron in hydrogen's energy level. I am going to be using a different color, in my case red, to represent the electrons that are in the outermost energy level. So that is hydrogen's outermost energy level, okay? And helium has 2 electrons in the outermost energy level. When we get to lithium, its energy level holds 2 electrons, and that is filled. And those I'm coloring in black. And then it has its second energy level, which holds 1 electron. For beryllium, 2 electrons in the inner energy level. In the outer energy level, we now have 2. Boron, 2 electrons in the inner energy level. Okay, and 3 in the outer. Carbon, again, has its inner energy level filled. 4 in the outer. All right. Nitrogen. And I know you know what's going on here now. You should be able to do this on your own. Oops, let's go back. Ugh. So we're at neon, has its outermost energy level filled. What you can do is you can pause this tutorial and go and fill in the last row by yourself. Okay, so here we are. You've made all your Bohr models. You're probably cursing me because you had to draw 18 of them. But I promise you it will help you understand some of the trends that we want to discuss. So the first pattern that you obviously already recognize, and I know this from discussions we had during chapter 4, is that the number of electrons in the outermost energy level equals the group number. So in group 1A here, we have 1 electron in the outermost energy level. In group 2A, 2 electrons in the outermost energy level. In group 3A, 3 electrons in the outermost energy level, all the way to group 8A, which are the noble gases, which have a full outer energy level. And we know that for helium, this first energy level, it just has 2 electrons, but it is full. And then as we go on through neon, argon, krypton, etc., down the periodic table, those have 8 electrons in the outermost energy level. Okay, so that's the relationship, and that's going to be important to us, is the relationship between the group number and the number of electrons in the outermost energy level. Okay, the first thing we're going to talk about is atomic size, and we're going to refer to atomic size here in terms of atomic radii, and the radii, or atomic radius, is the distance from the nucleus to the outer energy level of the atom. Okay, so it's just like the radius of a circle. If you're imagining the atom to be a circle, for our purposes, that's what we're going to do right now. In reality, it isn't. We'll learn about that later. But if we look at this and look at our trends here, let's start going down group 1A. Okay, and as we go down group 1A, what do you notice? That we are adding an energy level each time. So you can look at this and physically you can see that as we're adding electrons and we're adding energy levels, then the atomic radius would seem to increase, and it does. Okay, so as we go down the periodic table, like this, and I want you to do the same thing, okay? And this is hard for me to write on the side here. Atomic, make yours neater than mine. Radius increases, okay? Now, as we go from left to right on the periodic table, the trend in atomic radius is a little bit less obvious. It appears as you go across that it would get bigger and bigger and bigger. But that's not actually what happens. You'll notice that as you go across a period from left to right here, okay, and just follow my cursor, that we're not adding energy levels, we are adding electrons. And as we do so, we're also adding protons. And although I didn't draw those protons in the nucleus, I have the atomic number written here so you can see that the number of protons increases. So as the number of protons and electrons increases, their attraction for each other increases because you have more positives and more negatives. So you have this net greater attraction. So what actually happens is that this outermost energy level actually becomes more tightly drawn in and attracted to the nucleus of the atom. And I didn't draw it that way. It's actually really hard to draw by hand. But if I did, like these outer energy levels would actually, as we go from left to right, get closer and closer to the nucleus. So the atomic radius, as we go from left to right across the periodic table, doesn't increase, it decreases. And that is due to the attraction, the increasing attraction between the protons in the nucleus and the electrons. Okay, so when you guys did your lab and you measured and calculated the atomic radii of the 4 different metal atoms using those metal bars, you can actually plot those radii on your periodic table and you should be able to see a trend that follows or mirrors this one. And we will take a closer look at that in class. So overall here, we can see that which element would have the largest atomic radius. It would be sodium here. Sodium is down here. As we go further down, group 1A would get even larger. And as we go across this way, the atomic radius would actually be smaller here in helium. Okay. Our next trend, and I'm going to switch colors here to deal with that. Let's go with green. Okay. Our next trend is going to be ionization energy. And that is the energy required to remove an electron from the atom, and it's usually measured when the atom is in the gaseous state. Okay, so it's the energy required to remove an electron from the atom. In other words, it's the energy required to make an ion, right? So just think about it this way. Which elements on the periodic table would it be easier to remove just one electron? Well, it would be group 1A because there is only one electron in the outermost energy level. So it would take the least amount of energy to remove that one electron. As we go down group 1A, that electron is further and further from the nucleus. It's also further, what that means is it's further and further from the attractive positive force of the nucleus. So this electron here in sodium is experiencing less of an attractive force to the nucleus than the electron, for instance, here in hydrogen, because in hydrogen it's much closer to the nucleus. So the trend in ionization energy as you go down a group decreases. So the ionization energy, boy, I feel like a first grader right in here. Ionization energy decreases. That means it requires less energy to remove an electron from the outermost energy level, okay? As we move across the periodic table, as we move across a period from left to right, we have more and more electrons. And remember that those electrons in that outermost energy level, because the atomic radii is decreasing, those electrons are actually closer to the nucleus. So they're attracted more tightly to the nucleus. So it's harder to remove an electron. So what that means is that the ionization energy increases as you go from left to right here. And again, you should be drawing these arrows and labeling these trends on your own periodic table. It's harder and harder to remove an electron. So that's why the noble gases are stable. They have a full outer shell. It would take a tremendous energy to remove those electrons, so they have a very high ionization energy compared to the elements in group 1A. Okay, now in terms of ionization energy of lithium versus sodium, lithium would have a higher ionization energy than sodium. In other words, it's a little harder to remove that electron from lithium's outer shell than it is from sodium's outer shell, because that electron in sodium is further from the nucleus, further from the attractive forces in the nucleus than it is in lithium. So sodium will have that electron removed more easily. When we think of the term ionization energy, I always think of it like the energy required to make an ion, removing electrons to make an ion, a positive ion. And that's one way you can remember what that term means. The next trend that we're going to look at is electronegativity. And this is sort of the opposite of ionization energy. It is the ability of an atom or ion to attract electrons. And it's measured when that element is in a compound. So it's the ability to attract electrons, okay? And it follows the same trend as ionization energy. Okay, so let's draw this in first, and then we'll talk about it. So I'm going to do this in red. I'm actually going to put my arrow down here simply because I have room. You can put it up here or whatever, wherever it's best for you. So electronegativity increases. What this means is the ability of the element to attract electrons increases as you go across. Meaning that, for instance, these guys, it's easier for them to attract electrons. Now, I just made an error because I drew this arrow right into the noble gases, and I really did not want to do that. So what I'm going to do is grab my eraser. Luckily, I can erase. Woohoo! And fix this. So I'm going to draw this stopping right there. Okay, and the reason I'm doing that is because these noble gases already have a full outer shell, so they do not want to gain an electron. However, fluorine and chlorine have 7 electrons in their outermost energy level. It would only take one more electron to have a full outer energy level, which makes them really, really, really want to gain an electron. That means they have a high electronegativity here. Lithium and sodium have a lower electronegativity. They only have 1 electron here, so it would take a lot of energy to put more in their outermost energy level. Okay, whereas these guys, they only need 1 more, so that would require a lot lower energy. Okay, here I'm going to be drawing over my atomic radii, drawing here. Electronegativity decreases. Again, it follows the same trend as ionization energy. okay? Because the outermost energy level here in sodium is so much further away from the nucleus, the attractive forces between the electrons and the nucleus is weaker, so it would be much harder for sodium to gain electrons than it would, for instance, for lithium. Because its outermost energy level is closer to the nucleus, the attractive force between the electrons and the nucleus is greater. It'd be a little easier for lithium to gain electrons than it would be for sodium, okay? So these are the three trends. They are related to energy levels, and that's what you need to keep in mind here, okay? The other thing is our relationship between the group number, okay, and the charge when the atom becomes an ion. So I'm going to be drawing underneath here. You might, if you have room, want to draw this across the top. And I think I will choose gray. Let's see how that works out. Since we only have one electron in the outermost energy level in group 1A, in order to get a full energy level, the elements in group 1A will lose that electron. That means they have one more proton than electrons, so they will have a +1 charge as ions. Okay, so these charges here are dealing with ions. In group 2A, since we have 2 electrons in the outermost energy level, the easiest thing for them to do to become ions is lose those 2 electrons, and these would have a +2 charge. For boron and aluminum, they just have 3, so the easiest thing to do is for them to lose those 3 electrons and have a +3 charge. For carbon and silicon, they have 4. It could really go either way. We'll talk about this later, all right? Right now, for now, we're just going to put a +4, -4 to simplify matters, okay? For group 5A, they have 5 electrons in the outermost energy level. It would be much easier for these guys to gain 3 electrons to have a full inner shell. So since they're gaining 3, they have 3 more negative charges than positives, so they have a -3 charge. In group 6A, they would gain 2 to have a full outer energy level, so that's a -2 charge. In group 7A, they would just gain 1 electron to have at full energy level. That's a -1 charge, and as we know in the noble gases, this is a 0 charge because they don't gain or lose electrons. So just by looking at the periodic table and the representative elements, you would know the charge on any element when it becomes an ion. And so there's really like no memorization involved here if you have a periodic table available to you. It becomes very easy. So for instance, when we're writing sodium as an element, that's how we write it when it becomes an ion. It has a +1 charge. And when ions just have a +1 charge, it is just has been the procedure with notation just to write a positive and not the +1. Okay. For beryllium, for instance, there's the beryllium atom. Beryllium would have a +2 charge as an atom, as an ion, sorry. Boron as an element and boron as an ion. Okay, we're going to skip carbon for now and go to nitrogen as an element, nitrogen as an ion, oxygen as an element, or atom, I should say, oxygen as an ion, fluorine as an atom, fluorine as an ion. Okay, when these elements become ions, they actually take the ending IDE. So the sodium atom becomes sodium ion. And actually this applies, let's talk about the ions down here, the negatively charged ions. Sorry. Nitrogen atom becomes the nitride ion. Oxygen atom becomes the oxide ion. Fluorine atom becomes the fluoride ion. So in your negatively charged ions, which you will learn are called anions. Anions, this is nitride, oxide, fluoride. Okay. The positively charged ions are called cations. So let me differentiate this for you. I'll draw a line across here. These are cations. They're not pronounced cation. They're cations. These guys down here, negatively charged ions, are anions. So from now on, we're going to refer to these as cations. They are positively charged ions. Anions is negatively charged ions. So we'd name this the sodium ion, the beryllium ion, the boron ion, the nitride ion. Here the anions end in IDE. Oxide ion, fluoride ion. Okay, makes sense. Again, this would be phosphide ion, sulfide ion over here, chloride ion, because these form anions here, phosphorus, sulfur, chlorine in groups 5A, 6A, 7A. As ions or anions, their name ends in IDE. As cations, they do not end in IDE. So we've covered a lot of stuff here. We've covered some trends in the size of the atom or the ionic radius. We've covered ionization energy, the energy needed to remove an electron from the outermost energy level. We've covered electronegativity, the energy required to gain an electron. And we also covered the charges that occur when neutral atoms become ions within the representative elements, and then how we name these cations and anions. So I really think that you need to watch this tutorial more than once. That's why they're here, so we can review these multiple times. You do need to know these periodic trends and explain why they exist, and you need to know the charges of your ions. I want to make just a few adjustments here to this recording to clarify some things. And over here, when we were discussing ions, really in this label, this should not say element. I really needed to say atom, referring to a neutral atom versus an ion. Okay, so remember that when ions become positively charged by losing electrons, they are cations. So this is the sodium cation, the beryllium cation, the boron cation. When atoms gain electrons to become ions, they're called anions, and then they take the ending IDE at the end of the name. So we drop the original ending and replace it with IDE. So the nitrogen ion is the nitride anion. Oxygen becomes the oxide anion. Fluorine becomes the fluoride anion. So we have nitride, oxide, fluoride. Just to clarify those, I was hoping that you didn't have any confusion. I realize I might have caused some here with this mislabeling and then sort of my bungled explanation here. I want to also go back to carbon and silicon, and really carbon and silicon mostly have a positive 4 charge instead of negative 4, so cross that guy off here to clarify that as well. Okay, but remember that these trends are important for you to know. Their relationship exists because of their electron configuration, the number of energy levels they have, where the electrons are. One other term that I didn't discuss that is related is the term called shielding. And shielding refers to the distance really between the nucleus and the outermost energy level of the atom. And the greater the distance there is, in other words, the more energy levels you have between the nucleus and the outermost energy level, the greater the shielding you have. It means that the less attraction you have between that positively charged nucleus and the outermost electrons, because they're shielding caused by the inner energy levels. It's caused by the inner energy levels. So in sodium, for instance, there's a higher amount of shielding between its outermost electron and the nucleus, meaning that the attraction between that outermost electron and the nucleus is smaller, so it's easier to remove that electron. Hence, it has a very low ionization energy because of the high amount of shielding. Whereas the shielding in lithium is slightly smaller because it has one less energy level here. So there's a slightly greater attraction between that electron and the nucleus. So it has less shielding and a slightly higher ionization energy. So that shielding really refers and is related to the number of energy levels between the nucleus and the outermost energy level. What I want you to do is, when you're finished with this tutorial, is to define all of these terms that I put up here in your lab notebook. So I want you to go and define shielding, look it up in your textbook, look up electronegativity, ionization energy, atomic radius, okay, cation and anion, and write the formal definitions down from your textbook into your lab notebook. You can compare them to my explanations here to get a greater understanding. So you're going to have to do multiple review of this chart. Remember that to learn this, you have to be exposed to it more than once, okay? To get those neural connections to be made, you have to have some repetition here. So make sure that you review this in your textbook and write down those definitions.